Hello everyone, this is the video lecture of section 5.9, approximation of integration or approximate integration. So, why approximation? So, why approximation integral? Well, so far we were able to find the true value of this by using fundamental theorem of calculus, that is capital F of x from A to B, right? Capital F of B minus capital F of A, where capital F of x is the antiderivative. Well, what if you can't find antiderivative, right? So, can't get explicit form of antiderivative or indefinite integral, okay? Can't get it. Secondly, your lowercase f of x was not even given as an explicit formula. Or f of x is given numerically with numerical there. So f of x itself is approximate value and not given for all real number x, but some discrete value of x. Okay? For these cases, we have to use approximation. Okay? Now, in order to think about various approximations, we have to go back to the very definition of definite integral. So when you have, recall, so when you have something like this, what we did was we think about uniform partition, right? x1, x2, all the way to xn minus 1, xn, this x is 0, and let's say this is xi minus 1, this is xi, there will be ith interval, this is ith interval, and we choose sample point. So first of all, delta x is length of each subinterval, which is b minus a over number of interval, and we choose xi star from the interval. This is belonging to the interval, belongs to. This stimulus belongs to xi minus 1 to xi. So greater than equal to xi minus 1, less than equal to xi. So we choose any xi star. So let's say x1 star. x1 star. This will be xi star. So it doesn't have to be in the middle, anywhere in the interval, right? And then at those points we calculate function value and we use that function value as a so-called height. So when you have this, use these points as a height. At those points we use a height. And then we calculate these areas, right? At those areas up will give you Riemann sum, right? So sum of those areas, I from 1 through n, f of xi star delta x. Now that would be a good approximation for the area under the graph of y equals f of x. and above the x-axis, right? And if you take more and more, larger and larger n, which means more and more, finer and finer partition, then smaller and smaller error it gets. So in the end, if you take the limit as n goes to infinity, that is what we call definite integral. Now, even though we talk about areas, f of x may be negative, right? This will be some of the signed areas. A region above the x-axis will be added as an area. A region below, A1, A2, A3. Area A1, A2, A3 from A to B. Then the definite integral will be A1 minus A2 plus A3, right? Because in those areas, in those regions, your function value is not height, it's negative of the height. Delta x is always positive number, base width. So negative of this will be negative of the area of each rectangle here. So, because of this, if n is large enough, then this will be approximated by Riemann sum, right? Because limit value as n goes to infinity. So when n is large enough, that will be a good approximation. Now this will be good approximation. Now that would be called Ln if we use xi star to be xi minus 1 for all I. This, what is it? Upside down capital A is called for all I. So always, for every subinterval, we choose left endpoint. That's what L for left endpoint. Ln. Okay? This value will be Rn, right endpoints, right sum. If we choose always right endpoints, then we call it right sum. This is called left sum. This is right sum. Now this will be called, if we choose our sample point to be the midpoint between x1 and xi minus 1 to xi, midpoint, then we call it midpoint rule. We call it midpoint rule rather than mid-sum. Okay? Midpoint rule. Okay, let me just check the taping right now. All right. As you can guess intuitively, probably midpoint is better approximation than right endpoints or left endpoints. By going through midpoints, there's a overestimate, underestimate kind of cancel. It is supposed to get smaller error. And we'll see some of those. So approximation of definite integral using Riemann sum, then we use only midpoint rule because it is the best overall. So midpoint rule, that is, we are approximating definite integral. So n is number of subintervals, number of divisions of interval, and that is delta x times f of x1 bar xn bar, right? Where where delta x equals b minus a over n, and xi bar is xi minus 1 plus xi over 2. The midpoint of the ith interval, average value, midpoint. And of course, xi is a plus I times delta x. I runs from 0, 1 to all the way to n. See? X is 0, x 1. A plus 1 delta x, a plus 2 delta x, a plus 3 delta x. Alright? Now, there are other rules called trapezoidal rule. So this is it. Now review. When you have a trapezoid, base lengths A and B and height h, your area is average of the base times h. Okay? That is the area formula. Okay. Let me check the video. All right. So now trapezoidal rule is by using trapezoid in approximation. So when you have a graph like this, trapezoidal rule. So if you have a graph like this, let's say from A to B, let's say you're using 1, 2, 3, 4, 5. Then at each point, so let's say, and you make a connection using each point. You draw a trapezoid. Alright? And you add up the area of the trapezoid as an approximation of area of the region. Right? So trapezoids are not one of these Riemann sums, because Riemann sum is always base length times height using function values somewhere in the interval. This one is not rectangle at all. Riemann sum is sum of the bunch of rectangles. This is trapezoid. Okay? Again. So let's say this is x0, x1, x2, x3, x4, x5. Now think about it. So, well, let's say these are in general xn, even though it is 5, let's say. So when you have an n division, trapezoidal rule is the first area. What is the area? A1. We consider now these two vertical segments, line segments, are parallel because they are both parallel. So this is trapezoid, right? These two are bases, A and B. Average of those. So f of x is 0 plus f of x 1 over 2 times height, which is delta x. Right? Second one will be f of x1 plus f of x2. Base A, base B, average, base average times delta x as a height. Okay? So your sum of these areas of the trapezoid will be 1/2 times f of x is 0, f of x1 times delta x. plus 1 half of f of x1, f of x2, delta x. Third trapezoid will be x2 and x3, right? All the way to the last one. F of xn minus 1, f of xn, delta x. So if you add them up, what do you get? I can get delta x over 2, right? Times f of x is 0. Now f of x1 twice, f of x2 twice, f of x3 twice, all the way to f of x. 2 times f of x n minus 1. And then f of x n. The very end points only once. All the intermediate function values are twice. And then delta x divided by 2. Okay? So this is trapezoidal rule. Some of the areas of the trapezoid. Okay? Then now when we use approximate values for integral, we want to know how much of error is expected in the worst case scenario. All right? So normally both midpoint rule and trapezoid, obviously more the division, the better the approximation, which is less error. Now, first of all, what is error? The error is nothing but true value minus approximate value. Like exact integral value minus midpoint rule value. That would be error from midpoint rule. Now, true integral value minus trapezoidal rule value will give you error for trapezoidal rule. And the larger the n, the smaller the approximation. Error. The smaller the error we expect. Alright? So we define this notation. E for error, midpoint rule with n division. That is true value minus midpoint rule as we defined here. Alright? And then error due to trapezoidal rule is true value minus trapezoidal rule. Alright? Now, there is a theoretical bound, upper bound of the error for each method. THM stands for theorem. Theorem 1. Error bound. Error bounds for NN and TN. Now suppose that your second order derivative absolute value is less than or equal to some positive constant k on this interval. Okay? Then, see? So k is the maximum possible value of the second order derivative on this interval. Then, absolute value of error from midpoint rule will be less than or equal to this k times b minus a to the third over 12 n squared. Okay? And error from this is trapezoidal rule. Error from midpoint rule will be less than or equal to b minus a to the n over 24 n squared. It is very interesting. So this is 1/2 of this term. So this value is the maximum possible size of the error, the worst case scenario. Your actual error is almost always smaller than this, sometimes quite smaller. Alright? But anyway, this is in the worst possible case, your error will be this large. So this one gives you upper bound of your error. So if you have to design some structure, something, and if you want to decide the strength of a beam or thickness of beam, after calculating all the weights and the stress and strain, well, this is the one you're going to deal with, right? Let's say our calculated value of this stress and strain of this beam has to endure is this value, and this is maximum possible error, right? So using this, you have to estimate your value considering this one. Your calculated value plus maximum value error will be the maximum possible value of the strength it needs. And in civil engineering, they usually triple that, just in case. You know? To have a safe structure. Anyway, this is the worst possible value of the error for each method. And this one seems to suggest that at least worst possible case, midpoint rule has quite a small 1/2 value of the upper bound of the error of the trapezoid rule. So twice accurate, because error is 1/2 maximum possible error. All right. Now let's do some examples. Example 1. Approximate the integral 1 to 2 1 over x dx using a t5 b m5, and then b find c, and then find evaluate, and then evaluate error, maximum error about t5 and maximum error about m5. Okay, so this is function is 1 to 2. One to 2. So 1.2, 1.4, 1.6, 1.82. So 5 intervals. 5. Okay? So your x is 0. In this case, x is 0 equals 1, x1 equals 1.2, x2 equals 1.4, x3 equals 1.6, x5 equals 2. And delta x is the size of this each length, 0.2. Okay. Okay. And then T5. Okay, delta x equals 0.2. And T5 is, what is it? Delta x over 2. So 0.2 over 2 times function value at the end point 1 over x1 plus 2 times f of x1, 1 over 1.2, and 2 times 1 over x2, 1.4, 2 times 1 over 1.6, 2 times 1 over 1.8, and the last one, just a function there at the end, 1 over 2. So 0.1 times sum of these. If you do that, you're going to get about 0.695635. Okay? So that's the approximate value of the integral using trapezoid rule. What about M5? The M5 is delta x, which is 0.2. In that case, we need midpoint, right? x1 bar equals 1.1. Midpoint between this one and this, 1.1, 1.3, 1.5. So x2 bar, 1.3, x3 bar, 1.5, x4 bar, 1.7, x5 bar, 1.9. So in that case, your M5 is delta x, in this case, 0.2. And then times function value at x1 bar. So 1 over 1.1. Function value at x2 bar, 1 over 1.3. And you do the same thing for 3, 4, 5. Okay? And then calculate it. Then you get 691908. Now, what is, in order to get true value, error, we have to know true value. For this one, actually, we know how to get 1 to 2, right? Antiderivative is ln of x, absolute value, but we don't need absolute value because it is positive. ln of 2 minus ln of 1 is 0. So ln of 2, which is 0.69. 190, no, not 190. 3147. So error due to trapezoid rule is this true value minus this error. That will be minus 0.002488. And 5. 0.001239. Okay, I'm going to start. One. It's noisy. So, here, now as you can see, the error, this is actual error, right? Error from midpoint, error from trapezoid rule with the same n value. This is roughly half. Now, this is not the worst possible case. This is not the upper bound. This one says upper bound will be about half, and exactly half. And actual error is about half. So it's quite amazing to observe that actual error due to from midpoint rule is about half of the actual error from trapezoid rule with the same n value, not just the upper bound. Okay. Now, if you take a look at page 404, the tables. Take a look at page 404 in your textbook. They gave you approximate value from midpoint rule, trapezoid rule, and also left sum, right sum, ln, rn, all together. Now, what we are interested in is error. All right, the second table, E L-E-R-E-T-E-M. So error from left sum, error from right sum, error from trapezoid rule, error from midpoint rule. When n equals 5, 10, 20. Now, as you can see, error from left sum and right sum is definitely much larger than trapezoid rule or midpoint rule, right? For example, n equals 5, En was 0.001239, Et is minus 0.002488, but Er is 0.04, about 20 times larger than trapezoid, or 40 times larger than, almost 40 times larger than midpoint rule. Similar to left rule, right? Left sum. More important thing is that when increase from 5 to 10, look at the table. What happened to the error to the midpoint rule from 5 to 10? From 0.002, this is n equals 5. When n equals 10, you actually find that that value will be 0.000312. 0.000312. Yeah, 312. And this one will be minus 0.00624. Again, this is 1/2. But more important thing is that this is about 1/4. When the number of interval increases by 2, right? The number of calculation will be increased by 2. With twice the effort, your error will be 1/4. So it is a good deal, right? Same thing, 1/4. Actually, if you look at the table, when n equals 20, another twice more calculation, you get from 0 here 0.0007. Right? So it's another 1/4, isn't it? Also minus 0.000156. It's almost 1/4, right? Now look at this. These are all constants, fixed value. This is the only one you can control. Yes, 1/n squared. Even upper bounds of the error, inversely proportional to n squared. Okay? So, the worst possible case, upper bound of the error, was already suggesting that your error is, the error size in the order of 1/n squared. Okay? 1/n squared. But if you look at left sum and right sum, if you compare n equals 5, 10, 20, it's not going to be 1/4 each time, only about 1/2, right? So left sum, right sum is in the order of 1/n. If you put twice as effort, your error will be only 1/2. 10 times more effort, error will be 1/10. Here, trapezoid rule or midpoint rule, if you put 10 times more effort, error will be 1/100th. Alright? So it is a good approximation method. But this is not the method you're going to actually use in actual practice, like your calculator. When you try to find the numerical value of definite integral, you have to use, internally the calculator use some kind of approximation skill, but not based on midpoint rule. Even though it is good, but not good enough. Actually, the next method, that is, we call it, what is it? Quadratic. No. We call it Simpson's rule, based on quadratic approximation, is far better. That will be around 1/n to the 4th. So twice more effort, 1/18 the size of error. Okay? So we're going to do that one in second part of section 5.9. So this is the end of the first part of video lecture of section 5.9. Okay? Thank you.